to our treasurer, Chris Hamlin, because this is the annual meeting and he is required to do some treasury reports for us. Go ahead, Chris.
All right. Thank you, Dina. Everybody hear me okay?
Yes.
Yep, great. I really appreciate an opportunity to share with this group for a few minutes. I've got about 8 slides, and what I was hoping to do is impart upon this group kind of where the Denver Astronomical Society is from a financial perspective. And so I've got, let me just share my screen here. Okay, there we go. Hopefully everyone can see that. Yes, good. Like I said, I've just got 8 or 9 slides, and kind of what I was hoping to talk about today is I wanted to provide everyone with an overview from a financial perspective of 2023 and how things went. Talk a little bit about the different activities from a financial perspective that the DAS had. Also wanted to provide everybody with a quick summary of, from a financial position perspective, where we ended up at the end of 2023, just a month ago or so. And also wanted to introduce to the group some key financial indicators of the relative strength of the society, including some work that I did just recently to put together some financial health metrics for our nonprofit. And then I'd like to conclude with a little look ahead to talk a little bit about kind of what's on the radar from a financial perspective for 2024. So I'm not going to get into a whole lot of detail on this for obvious reasons. You can get lost in the numbers, but there is an annual financial report which I filed and posted today on our OneDrive, and that's available for anyone that would like to look at it in terms of the financials of the organization and kind of a historical view of what happened in 2023. So a lot of detail in that. I think it's 8 or 9 pages. But what I thought I would do is spare you the detail and give you some of the highlights tonight. Please do interrupt me anywhere through this discussion, and I appreciate the time. So just jump into an overview of 2023. If I was going to just kind of describe what happened financially to Denver Astronomical Society in 2023, I would say that we, struggled in 2022. Obviously, we were isolated and we weren't able to do as many of the things that our charter as we'd like to do. But after emerging from the effects of COVID in late 2022, the society has grown significantly, during the year in terms of membership. Just like Dina was mentioning, we've tripled or quadrupled the number of activities and events that we were doing in 2022. Our financial strength overall has grown significantly, and I'll get into some of the details on that. And then, just the level of our services that we're providing to the members in the community have grown as well. So a very positive, successful year for DAS, and I'm super excited to just share that with everyone. I mean, we're all in this group, we're all doing it, we're all participating, we're all benefiting from it. So obviously I'm not surprising anyone here. In terms of just some of the key metrics or key things that happened through the course of the year, I just wanted to call out that we had a very successful year financially. Just, if nothing else, just looking at how our revenues were, overshadowed our expenses that we had by $121,000. So that's pretty significant. Our assets during the year increased by nearly 51%. From $121,000, or sorry, by $121,000 to $359, almost $340,000. So very significant increase in the overall assets that we have as an organization. And we'll get into a little bit of this, but I wanted to mention that, I believe that the society has never been better positioned to do more in terms of additional funding and donations to charitable causes, and just to pursue the charter that we have as an organization. So it's a very exciting time. And, I think the growth of the organization, just in terms of membership, is a key indicator of that. So just kind of moving along, getting into a little bit of detail here in terms of financial activity. I just wanted to call out some of the kind of key things that happened during the year. In terms of revenues and income that was flowing in during the year, we had $189,000 of income from all sources. And listed below that here is a few of the key things that make up that number. Right at the top is donations. Obviously, we had some very significant donations, particularly to VNHA, over the course of the year at $108,391, which is very significant. In terms of public night, we had a much better year in 2023, in terms of public night revenues than we did in 2022, obviously, because we were outside of COVID, and over $7,000 in terms of revenues associated with public night events. The auction raised $5,208, very significant in terms of previous auctions. I think we doubled the one from the previous year. So that was great. And definitely we saw a large increase. I don't remember the exact percentage, but a very large increase in dues, correlated with the number of new members that we have. And even in 2023, we actually had sales of product, which was, at this level was a kind of a new development where we sold several hundred eclipse glasses and stickers related to the eclipses, and we're not slowing down. We've got sales coming on eclipse glasses even as we speak, and I'll talk a little bit more about that as well. In terms of expenses, overall, the organization had $68,000 in expenses, which is, fairly quite a bit more than the previous year. But then again, we also gave away much more in terms of scholarship awards in 2023 than 2022. As a matter of fact, $17,000, which, very significant. We had many member events. We had, I think, 4 banquets and 1 picnic. That as far as things where the books, the expenses fell into 2023. So we were doing a lot of things for members, and in terms of events, a lot of repair and improvements were made to the dark site in Chamberlain, and so we spent nearly $7,500 all told on those things in 2023. All part of our charter to continue to support those operations, and we certainly did that. And then the Astronomical Society, our website and the technology that it takes to support the organization, we spent $5,300 on that. Astronomical League dues, $4,700, and we did have a product expense related to the eclipse glasses, where we purchased 5,000 glasses and so a few thousand stickers and envelopes to go with it, and the total cost there is $3,300 or so. So, any questions about any of those revenues or expenses? No. Okay. Just in terms of looking at the financial position of the Denver Astronomical Society at the end of 2023, From a financial assets perspective, here's the details. I won't go through all the details. You can see it on the position report that's on the financial report that's available online. But overall, our cash on hand increased by 9.1% to $132,000. Scholarship funds increased 94% to $227,000. And as I mentioned, overall, the organization's assets increased by 51% to nearly $360,000 during the year. So really great year, ended in a really strong position from a financial position. So just wanted to touch on a couple, key financial indicators that really, indicate the relative strength of what's going on with our club. I've mentioned a few of these already. Our cash on hand increased 9.1%. I've highlighted that there. We actually gave 5 times more in terms of awards in 2023 than 2024 for the VNHA scholarship. Our overall revenues increased 48%, and the supporting expenses increased, but that would be expected given the increased activity through the course of the year. But the real, I guess the thing I really wanted to share with this group is the fact that as an organization, as a nonprofit organization, we are extremely strong. And what I did was I put together some metrics that are commonly used to kind of measure the strength of a nonprofit organization. And, in a sense, it's a type of scorecard, right? And these are all measures that virtually any nonprofit organization is measured against. Liquidity, the relative expenses of the programs that they have, level of liabilities, and last but not least, the ability to invest, and that is to invest in the charter and promoting the charter and in giving to other charitable causes and things such as that. And so overall, I indicated in the color there, and you can see the metric that goes with year by year. How do we match up? What's our report card? And financially, I'm happy to say our report card is virtually straight A's. And 2022 was a kind of a rough year, and we had a few trouble spots there, as you can see highlighted in the yellow. But overall, these measures are very strong for Denver Astronomical Society. And I guess if you look at particularly the ability to invest, you see a couple measures down there, which I'm super excited about, and we're going to have more discussions about with the board. But the number there and under 2023, ability to invest, the net margin ratio, that 18.2% basically indicates that after we've done all the things that we did this year or in 2023, we still have liquid assets available to invest in additional programs, additional support of other charitable organizations. And as a matter of fact, the calculation that I got was we had over $9,000 that we in 2023 that we could have applied to discretionary type spending on other causes and programs. And it's all driven because of the fact that our membership is growing and we have a large stable base of recurring annual dollars. So hopefully I can paint a picture there of overall that there's a lot more we could do, and we just need to know where to point the where to put our wallet, so to speak. Any questions?
Chris, this is Mehmet. Correct me if I'm wrong. The financial strength comes from the increase in membership, obviously, but also from one particular dear member's donation that came in after we lost him. I think it would be appropriate to acknowledge that, if I'm correct.
You're exactly right. And these numbers, though, there's a lot of detail behind these numbers. And one of the things that these numbers do not reflect is any assets that are not restricted. And any donations or any assets that we have associated with VNHA those are restricted, and we can't use those for general club expenses. So these calculations don't include those. So this is just the ongoing operation of the organization. So these stand on their own, but you're exactly right. We definitely should acknowledge the very large donation that was, the $100,000 donation that was given to the DAS, but ultimately that was put into the VNHA restricted fund, which we won't have access to overall as an organization.
Okay, thank you, Chris. I can't see everyone right now while you're sharing, so I don't see if there are any hands up online. If you would
Okay.
end your screen share, and then I could see if we have any other hands up.
I just had a couple closing thoughts, if I could.
Oh, yes, please go ahead.
Yep. I just wanted to mention that kind of what's from a financial perspective, what's kind of coming down the pipe a little bit here in early 2024 is the development and the adoption of an annual budget, something we haven't really had much of to speak of truly in a rigorous fashion in the last few, or at least as long as I've been involved with the financial side of this. And so we've got a draft budget, and I'll be sharing that with the board, and we'll be trying to get us to start leveraging that as a strategic tool. I also, as part of that, we will be able to identify and use the discretionary funds that I was just speaking of, that what's left over potentially that we could be investing in different ways and be, in more in more ways than we have been in the past. And that's a great position for us to be in. So we'll be talking more about that. And then lastly, I wanted to mention that, we are aggressively pursuing the sales of eclipse glasses as the April solar eclipse approaches. And we've actually established a e-commerce site for the sale of those glasses. If you haven't been out there, it's a great little site, and we're actually promoting the sale of the eclipse glasses through Facebook, social media, and particularly in the areas, we're doing it geographically in the areas where the eclipse will be in totality. So if you have any friends, colleagues, family, that please direct them to our website. We are taking orders and shipping orders every day. So I just wanted to make sure everybody was aware of that. So any questions? Okay, then I will stop sharing. I appreciate everybody's time. Sounds like there aren't any questions.
I'm looking at the second screen here. I don't see any. No, I don't see anybody with a question. Did you want to talk at all, though, about the investment strategy? I know you and John Grobert had talked about that recently.
Sure, I can spend a couple minutes on that.
Okay, please do.
John Gruber and I and the VNHA committee have been investigating, given the recent, particularly the recent large donation that we received to that fund. We have been looking, kind of reviewing the investment strategies that we've had in place for the last few years for those assets. And in particular, we've reached out to LPL, which is the firm that manages those assets for us, and asked them for an updated recommendation on how we should best invest those funds, given the requirements that we have of giving awards every year, and only a certain percentage of the incoming growth can be used towards those awards and things such as that. And so there's a need for some short-term liquidity as well as long-term growth. And we got some recommendations, and as a matter of fact, we'll be sharing those recommendations with the committee here. I think John set up a meeting here for the next couple weeks. But unfortunately, what LPL provided us was not, in our mind, particularly John Gruber and I's, was not what we thought was sufficient for the needs for the society. So we've kind of developed some alternative strategies that we are going to propose as well to the committee, VNHA committee, at that meeting. But we are, we're taking a fresh new look at it, and we will be, with the approval of the committee as well as the overall committee approval of the DAS board, we will be moving forward with making some changes in that area, which hopefully will allow us to provide even more scholarships every year in the future. So.
Okay, very good, thank you. And I think what Mehmet was getting at there, and some of you may have realized this, because we changed the name last year from VNH to VNHA. The large donor was the estate of John Anderson, who passed away last year. He made a bequest in his will to leave $100,000 to the Van Natten Hansen Scholarship Fund. And as a result of that, John Grobert made a recommendation, and the executive board agreed to change the name of the scholarship to the VNHA Scholarship Committee. So we're very grateful for that. John Starter was here many months ago to actually present the bequest, and we are very, very grateful for that. That has enabled the VNHA committee to greatly expand the amount and the number of recipients, so that we can expand that program greatly. So it's a wonderful thing. But we lost a dear friend. At any rate, okay. Joe, if you would like to come up and announce our speaker, we will proceed with that part of the meeting. Thank you.
Sure. Dr. Hart, are you there?
I am. Would you like me to share my screen?
Yes. Let me introduce you to the society.
Sure.
Quyen Hart is a PhD scientist with nearly 25 years of experience in astronomy, outreach, and education. As the project scientist for Webb Science Communications at the Space Telescope Science Institute, Dr. Hart leads Space Telescope's public outreach efforts for the mission. This role includes managing the portfolio of public engagement projects and leading efforts to identify, conceptualize, and translate complex science concepts and results into outreach products, activities, and events. Dr. Hart earned her PhD from the University of Colorado at Boulder, where she conducted multi-wavelength studies of active supermassive black holes and clusters of galaxies, and studied the X-ray emitting intra-cluster gas and clusters of galaxies. Oh, you can't hear? Okay. Her experience in astronomy outreach and education includes working on NASA's Universe of Learning and Outreach efforts for Hubble Space Telescope, James Webb Space Telescope, and future Roman Space Telescope at STSCI. Teaching physics and astronomy at Regis University, organizing and hosting outreach events, and directing summer STEM camps for middle school children. She is passionate about sharing the wonders of astronomy and science to the general public because she knows that everyone can be a scientist. Please welcome Dr. Quyen Hart.
Thank you very much, Joe, for the warm welcome. It's been great listening to the beginning of your meeting. Thank you so much for having me tonight to talk about the James Webb Space Telescope. I will sometimes interchangeably use JWST, I might call it Webb, but I'm talking about the same giant space telescope that is 1 million miles away from Earth. So that future is here. We are making the science discoveries now with the James Webb Space Telescope. Now, earlier in your meeting, I heard all these things about please volunteer and do outreach with these communities. And I just want to, when you guys were talking about that, I had to kind of bring up slides that I use when I talk to folks about how I got to be doing what I'm doing now. I've had a very long journey, an amazing journey to eventually get to where I am today. And it started way back when I was little, working in science museums, talking to outreach people at the museums, there's a picture, I went to Villanova University. So I did outreach nights. I didn't know any star in the sky. I just followed the person along and I knew how to work the telescope. But when I went to San Diego State University and got my master's degree, I actually had to run the planetarium for my classes and do star parties at night. And that's when I learned the constellations. And it was an amazing time. So for you all out there doing outreach with your telescopes, that's a piece that I miss a lot because I don't do that often anymore. But it is a time period in my life that I really enjoy. And the Astronomical Society is a big part of that. I've done a lot of teaching. I spent almost a decade at Regis University teaching with Fred Gray, who's in the audience, teaching astronomy and physics. I graduated from CU Boulder before then with my PhD there. So Colorado is near and dear to me as well. And you can actually see some of my outreach events that happened on campus where you are there. And you can see Fred there with during one of the partial solar eclipses. So outreach is something that is extremely important to me. I'm very passionate about it, and it has led me to where I am here today. As Joe mentioned, I've done astronomy research. It's a little far afield now, but I did do work on binary stars, clusters of galaxies, and supermassive black holes, active ones, and clusters of galaxies. And in my new role as the project scientist for Webb Science Communications, I actually started a few years ago doing outreach for the Hubble Space Telescope, James Webb Space Telescope, the future Nancy Grace Roman telescope, and did lots of different activities and have been able to be a part of this journey that the whole world has been taking in learning about the amazing technological marvel that this observatory is. So let's get started talking about the James Webb Space Telescope. It is a feat of engineering. There are so many new and innovative technologies that made Webb's ambitious science goals possible. It is an infrared telescope, if you weren't aware. It is not a Hubble Space Telescope that observes in the ultraviolet and in the visible and a little bit in the near infrared. Webb is almost completely sees in the near infrared and the mid infrared. In terms of size, it's quite large. You could, if you imagine the Hubble Space Telescope, its mirror, I could fit it up against your living room wall. It's just about 8 feet high. The James Webb Space Telescope, I would need a 2-story building to put that against if I needed to. So it's almost 20 feet tall there. So when did this launch? Some of you probably have memories, such as many people in the world, watching this launch on Christmas Day 2021. The launch here was very early in the morning on the East Coast. Christmas morning, we all got up, we watched, and a lot of us were so happy to see that it launched. And then surprised with the beautiful image of it going off into space to a journey 1 million miles away from the Earth. So that's about 4 times further away from the Earth than the moon is. And that is our last picture of the observatory as it was going on its way. 30 minutes after launch, the controls for the observatory were transferred to Baltimore, Maryland, to the Space Telescope Science Institute. We are the Science and Mission Operations Center for the observatory, and it is commanded from there. In fact, the commands leave Baltimore, and then they are relayed through the Deep Space Network that then go up to the observatory, and then the observatory will send information back down through the Deep Space Network, and then that information is all stored at STSCI, Space Telescope Science Institute in Baltimore, Maryland. So yes, there's a very expensive telescope that's observed 1 floor up from my office in Baltimore here. So this has been an amazing feat, an international feat with NASA and its international partners, CSA and ESA, and as well as many industries around the world here. So what allows us to observe the universe with Webb? There are 4 science instruments. You may have heard about those. There's one that's called the NIRCam, the near infrared camera. There's MIRI, the mid-infrared instrument. There's NIRSpec, the near infrared spectrometer or spectrograph, I mean, and NIRIS, the near infrared imager and slitless spectrograph. And you all are very familiar with the fact that telescopes can take pictures, images of space, but in this case, it's sensitive to infrared radiation. But you also know that light can be spread out, and you're able to take a spectrum. So I'll get through that in a couple of slides here. So a lot of people ask, how's the observatory doing? Do you really know? Well, it's not a secret, and I'm going to give you some key updates. So the American Astronomical Society meeting happened we're in February, so last month in January. And we always have a JWST town hall where the project scientists give some updates. And I thought some of these pieces would be interesting for you all. This is all public information. I will share with you where you can find the more detailed information. We're well into our 2nd year of science operations. So yes, JWST launched on Christmas Day 2021, but sorry, I meant to put a timer on real fast here so I know I'm going to go over time. But it took 6 months it took a month to get out to the Sun-Earth Lagrangian 2 point. And then it took 5 months for to turn on the lights, not the real lights, but make sure all the instruments are working, making sure they're cooled down and everything is behaving as expected. So that was all commissioning. And then the instruments, each individual instrument was commissioned to make sure it's working as well. And in the month of June, there was a series of observations that were called the early release observations, or the EROs. That was a language that we use, but you all know it as Webb's first images and data, which was released on July 12th. That was the beginning of science operations, because that's when we knew that all the instruments were ready to do the science that the astronomical community proposed and had approved programs to do. And so we're going to come up on that 2nd year anniversary this coming July for 2 years of science operations. It's doing so well. It's fulfilling the promise of revolutionizing science. And I'll go through some of those pieces in a little bit. To date, there are over 700 scientific papers that are based on that JWST data that have been published. Overall, the observatory is performing it's performing so well. The optics are more stable than is required. The sensitivity of the instruments is better than expected as well. Now there's a yearly cycle call for proposals, and the cycle 3, right now we're in cycle 2 of observations that were selected last year. Cycle 3, the proposals were submitted and 1,931 submissions were obtained. And that is the largest volume of proposals for any observatory to date. So it was a groundbreaking record for this third year of cycles. So the Telescope Allocation Committee has been meeting, and so lots of people will be anxiously waiting to see if their proposals were accepted in a few weeks or not. That they'll find out. I do not know. All right, so what are we trying to do with the data from this telescope? It's really to understand the story of us, really. How do we get from this picture? So the picture that you see here is the cosmic microwave background radiation. It is the first baby picture of the universe when light was able to stream unimpeded through the universe. Now that light has been moving through space, and the universe has been expanding, so the wavelength of that light has been stretched out all the way into the radio. And this is a very simple picture of the universe, where there are pockets of higher density and lower density. In this case, it's seen as temperature, but it really corresponds to density fluctuations. And the universe was only composed of hydrogen and helium and a little bit of lithium, and it was hot. But out of that grew, the gas came together, formed stars, formed the first stars, formed galaxies, formed supermassive black holes at the centers of those galaxies, came together to form clusters of galaxies. And the stars in those galaxies form star systems and planets that could, who knows, harbor life. We know of one, ours here. So how do we get from that simple picture to us? Everything that needs to happen, what is that story, and how can we learn more about that? Because that story is not a complete story at all. We need to understand where those complex elements in our bodies, what makes life, carbon, oxygen, nitrogen, how is that all arranged into complex molecules? Now, when you look at the periodic table in this graph here, so this is a way to have a snapshot of how do the elements in the periodic table, where do they come from? So if you look at the color coding, and we'll go through them all right now, but again, like out of the Big Bang, hydrogen, helium was only created. But where do heavier elements in the periodic table come from? Exploding massive stars, what you see in green, there's the proportions. Those elements come out of those massive stars exploding in supernova. How about exploding white dwarfs? There's a certain subset of the periodic table where the contribution comes from those objects, as well as low mass stars too. So getting a census of stars and how those stars live and die give us an idea of where these chemicals can come from, but then also to try to find them in space to eventually form in planetary systems like our own. So another reason why we want to use the James Webb Space Telescope is that in order to look out, every time we look out into the universe, we look back into time, okay? So we want to push further and further in time, or look further and farther away to get a glimpse of that. This is a data visualization using the Cosmic Evolution Early Release Science data. It's a deep field fly-through. This is the first data visualization that we released based on knowing the distances to these galaxies based on their colors. And so you're flying through these galaxies. You see that they have some really already shapes to those galaxies. But as you get further away and see further back into this image, the galaxies are more distorted. And then we see the very last image in here. We just fly to this one galaxy called Maisie's galaxy. It is a galaxy that we're seeing when the universe was only 390 million years old after the Big Bang here, when the age of the universe is 13.8 billion years. So the reason why we take pictures of the deep field is because in order to understand how galaxies evolve through time, we need to really get a snapshot of galaxies through all different kinds of time, because we can't sit and stare at one galaxy at and then watch it evolve over time. So we look at the nearby galaxies to see how they what they are like now. But as we push further out into the sky with our different telescopes, we can get construct that history of galaxy formation over time. But the piece that has been missing has been this very first chapter. If you think about how galaxies evolve as a book, we have everything but the beginning chapters. We don't know how it all started with the first galaxies themselves. And that is one of the main reasons why we need the Webb Space Telescope, because Hubble only can see so far based on its sensitivity. It cannot see any further because the light of those galaxies in the hundreds of millions of years after the Big Bang, the expansion of the universe has actually moved most of the light and stretched it out all the way into the mid-infrared, which is not visible, not detectable by the Hubble Space Telescope, and is only detectable by the James Webb Space Telescope. And so that's what we've been doing. The different scientists have been doing this with staring at different parts of the sky. This is a section of the JWST Advanced Deep Survey called JADES. And in this survey is one of the most distant galaxies that exists. It's about 13.2. It's a redshift of 13.2, and the universe, I don't have the number off the top of my head. I think it's about 390 million years after the Big Bang. And that's just one galaxy, but let's take a whole census of galaxies in this field and some other deep fields. What is Webb showing us? Webb is showing us that there are more bright galaxies in the early universe than we expected. We can actually find and weigh the supermassive black holes much further than we have been able to do before. We can identify some of the earliest structures that have been formed by where areas of higher density, in this case dark matter, clump together to form some of the first galaxies. So some of those earliest structures we're starting to see too, as well as looking at the chemical enrichment and even complex molecules in dust. We're starting to see all of that. Webb, these observations have not broken the universe or the Big Bang, or even found galaxies that are too massive. There are different things in the early days when these JWST observations came out. The data was new. People were trying to understand what they were seeing and understand the quality of the data, what kind of calibrations. So, like I said, we're almost done. We're almost finishing 2 years of science operations here. And so the science community has learned a lot. And a lot of the different things that astronomers have been seeing, they can, if we think of a model this way, it can be explained that way, but it does not break cosmology. But a lot of the photometric redshifts, like using the colors, are becoming very reliable as a good first estimate of the distances to these galaxies. But spectroscopy, as I said earlier, you guys know a little bit about spectroscopy. Spectroscopy is really how we know the distances to these galaxies. So for those of you who are not aware or know about spectroscopy, you know that sunlight, if you pass it through a prism, you can create the colors of the rainbow. Well, you can do this to infrared light. You can do this to ultraviolet light if you have the right disperser. And so the different colors of the rainbow are just really different wavelengths. And depending on the quality of your disperser, you can really fine tune how much you spread that out. Now, the interesting thing is in the details of the spectrum. So matter and light interact with each other. And so when this happens, electrons, we're looking at a simple model of an atom here, and electrons that are bound to that atom, they can make very quantized jumps in between energy levels, either to absorb light to go to higher energy levels or emit light going down to lower energy levels that are very specific to those atoms or molecules or isotopes. And so we can really look at those features in labs to be able to identify those like a barcode, like a fingerprint that really identifies that particular element. So we can do this not only in the visible light with things like hydrogen or helium or neon, we could do it with carbon dioxide, water molecules, or even complex molecules that we don't quite understand, like polycyclic aromatic hydrocarbons, or PAHs, which is one of, it's like sooty-like material that might come out of, a car engine, like the tailpipe. But those PAHs, or I like to say PHs, but some people say PAHs, that is picked up. The emission from those molecules rotating and vibrating can be picked up by the spectroscopy from the James Webb Space Telescope. And so we're really interested in those features from colder things, from dustier things. Spectroscopy also allows us, just like you hear the frequency of cars changing if it's approaching you or going away from you, light also can have shifts in their wavelength or frequency because of the motion, the relative motion between you and it. And so that allows us to do many different things about studying the relative motion. That includes watching, a star go around another star, or a planet going around a star, or a galaxy moving away from us, or gas going around a supermassive black hole. That's all relative motion, and we can see the signals of that motion in the fine details of the spectrum, the spread out light of the object that we're looking at. And so we call that the red shift or the blue shift, depending on if it's approaching you or going away from you. So how do we do this? This is how we find supermassive black holes out there in space. They have very unique signatures that are different than just signatures due to star formation or just regular old gas. AGN, active galactic nuclei, or active supermassive black holes here, really have telltale signs that they are there. And so this is looking at spectra taken with one of the SEERS programs. So that deep field that I was showing you earlier, that was just a portion of the deep field that was being visualized, but it's actually a quite large field. And so we can see the clear signatures of hydrogen, of oxygen, of what else is on there? Iron. When you are in science conferences and people put up their Webb spectra, that is when you hear collective gasp from the audience, because this just was not, this is not the way it was before JWST came along. And people are just amazed that things in spectroscopy appear clear as day. There's no denying that you see a signal that is related to a supermassive black hole here. In fact, in this field here, SEERS 1019, which is when this existed when the universe was just about 570 million years after the Big Bang. It weighs in at about 9 million solar masses. And you might say, how do we figure that out? Well, this is spectra from the observatory taken with NIRSpec. Now, NIRSpec actually has something called a micro shutter array spectroscopy, where it can take loads of spectra at once. And there's all these little shutters that can go on and off depending on the field. It's pretty amazing. I'll show you an outreach product that allows you to understand that, because these are really sophisticated pieces of equipment here, and the scientists are learning how to use it. Now, this spectrum of this galaxy here, what you see is, to fit the data that you see there in that plot, you need to fit it with two components. One component is the gas that's in the galaxy itself. So that picture, that inset, you can see that galaxy, looks a little clumpy. So what's at the center? What's most of the galaxy? Well, if you were to only model that using the gas in the galaxy at that redshift, it isn't quite a good fit to the data. But when you then fit it with faster gas that might be going around a supermassive black hole at the center, then the data is fit really well. And knowing when you have gas going around a disk around a black hole here, and that emission, this is hydrogen in this case, is emitting light. Well, you'll have one part of the disk moving towards you and one part of the disk moving away from you. So you get what is called a broadened line, where you get a red shift and a blue shift that broadens that out. And so the shape of that line can really give you an estimate of how fast that is moving. And if you know how fast it's moving, you can get a sense of the mass of the supermassive black hole. And that's how that's done there. So there's really highly detailed data here from spectroscopy. And that really is what astronomers are really excited about. We love the images, but we love spectra even more, allowing us to look at black holes and get a census of black holes in the early universe. So we're just starting to see the iceberg of the the types of black holes. So what you see in the purple haze, so here's a plot where there's the black hole mass from 100,000 solar masses all the way to 100 billion solar masses. What you see in purple there, I'm sorry, the x-axis is the age of the universe. So early in the universe is on the left, older in the universe, later in the universe is on the right. And the purple area are the types of black holes that have already been detected by other telescopes. So what you're seeing here is that the Webb Space Telescope can find lower mass objects that are in that later time, but we're also finding lower mass black holes at really early times. In fact, we're finding lots of accreting supermassive black holes in the early universe. And to grow into the to grow into the masses that we see here, will it require really high accretion rates, or do we need bigger seeds to actually start these black holes? And so we're just getting a tip of the iceberg of trying to understand how black holes are created. Could this be pointing to the prediction that black holes actually collapse out of a cloud and not form stars at all? Maybe. We don't have enough information. But the thing is that what's important here is that the data that we're just getting now is helping us to try to answer those questions as we get more data. And this could even revise how researchers understand how black holes are forming. Now, the wonderful thing about the James Webb Space Telescope is that it's got all these other telescopes that are also observing the universe. And so by leveraging multiple telescopes, we can even push the limits here. So actually, this is the furthest black hole that has been detected by both the Chandra X-ray Observatory and the JWST Observatory. And I apologize, I don't have the distance in front of me. But what you see here is a galaxy cluster, one of my favorite topics, a cluster of galaxies, which is the baryonic light in what you see in white here. In this case, it's infrared observations from JWST. What you see in purple is the color assigned to the X-ray emission from the intracluster gas. Clusters of galaxies actually have more dark matter, about 10 times more dark matter than baryonic matter, the matter that you see in dust and starlight. And the gravity is so strong from all of that mass combined that it actually bends space and acts like a magnifying glass. And so this galaxy in the background is magnified due to the lens of the cluster itself. And so there's an X-ray source that is really bright in the Chandra observations, but looking at other images, they couldn't find a counterpart to it until they realized that JWST had looked at it. And so they found the counterpart, and the combination of that data set allowed them to figure out the distances. So using the combination of different observatories to really understand the universe, people are adding in JWST into to existing data sets here. So the black holes that we're finding, they are more massive compared to their galaxies than what we see in the local environment nearby. So they're all more massive than we expect them to be for that given mass. So this could be that pointing to the evidence of, did they form directly out of clouds without any new stars in that early universe? Was it really effective and efficient? It's just really too early to see that, because maybe we're just seeing the outliers of that. So again, getting more data to really understand that. So this is a place to keep your ears out for how are black holes forming in the early universe, and what are the galaxies doing in the early universe too. I had mentioned, the structure in the universe coming out of that CMB, the cosmic microwave background radiation. The first stars had to form. The first black hole seeds had to form. Galaxies had to form. And then clusters had to form. So we're getting a glimpse of the first proto-clusters. So this here is a foreground cluster in Pandora's. It's called Pandora's cluster, but the red images there are galaxies that are actually behind it. But when we do diagnostics on how massive they are, what's their redshift, what's their velocity relative to each other, we can sense that it's a protocluster. They're going to probably group together. More galaxies going to form and collect together and form something maybe like the Coma cluster. And so this gives a sense of how early did these large clusters nearby form in the early universe. So it's really, before Webb, we couldn't really explore this regime, this time regime. Now, getting back to the beginning part, remember this, why do we want to study the universe? Figure out what is our story? How did the galaxies form is where where we were just talking about, how the supermassive black holes. Now, in all those galaxies are stars, and some of those stars will go supernova. And the question is, can dust survive in a supernova? So the image that you have on the left here is a Webb mid-infrared image of Cassiopeia A, a supernova remnant. And then there's the Hubble image on the right. It looks much richer in the JWST image because we're seeing the dust, whereas the Hubble image, we're seeing the shocks from the explosion, the shock wave plowing into the surrounding material that was sloughed off by the massive star before it went supernova. So we know that in general, we need dust to form the things that we see around us, the planets and the stars and the different things in our solar system. So we need a really complete dust budget to understand where did all the dust get created. Is supernova one of those places where it can be created? But the question is, can it survive? I mean, this is one of the most explosive events in the universe, and you would think that dust does not survive. Well, it looks like dust does. And so you see everything here unfolding as it did in the past, 340 years ago, from our perspective on Earth here. It's a fairly young supernova remnant. Let's see here. And you can combine the observations with the Chandra X-ray Observatory too. And you can see in the middle of this image on the left here, there's kind of a green blobby monster in the middle. And the scientists just recently were trying to understand the components of what they see in the dust of the mid-infrared image and compare it to the sources of shocks and filaments that they see in the X-ray image. And they got a sense, they're all, yeah, this is it's dust from a shock, but it's in the foreground. So that's been really interesting. Now, this is a nearby supernova, and dust is in this supernova remnant. How about far away? Cool, it's not going. There you go. Okay, so this is NGC 6946. It's located about 22 million light years away from the Earth. People have nicknamed it the fireworks galaxy. And there's 2 old supernova in this galaxy. So the question is, did the dust survive in this galaxy that's far away from us? So not a recent or nearby. And sure enough, when you take an image with the James Webb Space Telescope using the reddest filters, the MIRI filters, it is glowing. There's dust there. It's surviving. And so this is a reservoir of dust in the universe, these supernova explosions, but those only happen for the most massive of stars here. And you might be interested, like this is an image that you may have seen, but you might see, wow, this is not exactly the way I see it in press releases, because I see the filters listed on the bottom. It tells me it's MIRI. It tells me which filters. It also gives a scale bar. So for every image that is in a press release that we create out of the Space Telescope Science Institute, we also lead the news. And so my coworkers do the news. And I'm involved on the outskirts a little bit. But you can see there's a scale bar there. So if you're ever curious about the scale of any image, if you go to the download details page for every image, there's always a compass image. And so you can see what's east, what's in this case, yeah, east and north. Some people don't know that. They're like, oh, what filters, what exposure time? It's all there. I'll show you later. All right, so that's dust and supernova remnants. Now, other pieces to form planets and moons and things, we need ices too. We need complex molecules. So we see that when we look at dark clouds in the infrared. This is the Chameleon-1 molecular cloud. It's a really dense cold region where stars are forming. The observations here in the near infrared really give us an inventory of some of those coldest ices to date in that cloud, such as some organic molecules, carbonyl sulfide, ammonia, methane, and methanol, one of the most simple organic molecules. So this really gives us a result of what happens when there are dust grains that are already out there. And what can happen to the chemistry of those things? Can ices form on those? And eventually, that cloud will form stars, and those stars will form planets around it. So what are those initial seed locations for where star formation can happen at this extremely early stage when it's still really cold? So it gives us ideas on the pathways, like how do these simple and complex molecules form? In this case, we actually use the scientists use the background stars to let the light go through the cloud, and they did spectroscopy and looked at absorption features. So as I said earlier, it's really, really interesting. The images are stunning. There's no doubt, but the spectroscopy tells us what it is. And so the spectrum of this chameleon cloud is where the ice chemistry is determined. And you guys can see the dips in there. They're clear as day, right? Those are features of water. I can't see it up close here. Of water, carbon dioxide, carbonyl sulfide, and methanol. And the spectroscopy gives us the details of what's happening in this place where stars will form, like this very famous object that everyone is familiar with, I hope, the Pillars of Creation, M16. So this is the Hubble image. And I wanted to tell you stories about, the different, so some of the things that happen at work here. And so I love this image. Everybody loves this image. But what does it look like with Webb? So here we have a near infrared image of Webb where the filters, the near infrared colors are assigned in chromatic order. So the shorter filters in the infrared are assigned bluer colors, whereas the redder filters are assigned redder colors here. And you're seeing star formation. Before, with the Hubble Space Telescope, you could see the dark cloud, but you couldn't see through it. You couldn't see the other stars that were embedded inside it. But as soon as you go to near infrared, you can see it's dazzling with stars. Those are all stars in this star forming region. But even then, the dust clouds are not, they're still too dense for you to peer into them with the near infrared. But if you take a closer look, whoops. So if you take a closer look here, I'm just going to check the chat here to make sure there's nothing. Okay. If you take a closer look, these ends of those pillars are where young stars are forming, but they have jets like we see other jets in other star forming regions, and they are impacting the cloud, and it's glowing with infrared light. Everything is glowing in here. It's not a reflection nebula. It's emission from a lot of PAHs. And you can actually see some of the jet coming out of here. If I zoom in on another part of the pillar here, you can start to see, you can't see the embedded star at the tip here, but you can see that there is a really red feature again. These wavy lines that look like lava, they're ejections from that star that are still forming. Now, if I move into the mid-infrared, what you're going to see is the scene looks a little bit different. That's because in the mid-infrared, you start to actually see the dust itself glowing. So even in this case, some of the parts of the pillar are so dense that there is no emission there as well. But the scene is no longer dazzling with stars. That's because stars don't emit that much in the mid-infrared. And you do have some embedded stars here that are glowing. So the scene looks different. It lets you understand these regions of star formation. My jaw dropped when I saw this image. This is an image that we put out as an outreach image. And so I'm on the team that does this. And it's that when you see things for the first time, it's it's a very, you don't forget that moment. All right, so let's see. Other areas for looking at understanding, this is also an outreach image, looking at L1527, this is actually a protostar. And so you see two outflows here where the material has been carved out, and you can see the emission from the dust in the infrared here. And you can actually see, if we zoom up in the center there, you can actually see a little disk there, which is the accretion material around this protostar. Now, with the imaging with the James Webb Space Telescope, we're starting to really see the dusty features around objects like Fomalhaut. So this is a star that you can easily point your telescope to. You will not see this, but you can see that star, and you can wonder, well, what's going on here? We need to, now you have all that dust that might have come out of the supernova. You have ices that are in those star-forming regions. So how do they eventually collect into these disk around stars that have hydrogen and helium and all this other complex molecules? So we need to study targets like this. Now, this is really a later stage of planetary formation, but most of the planets are probably already formed in this, and it's getting towards that period of bombardment. If you understand the history of the solar system, which planets were formed, but then there was a bombardment period. Now, what you're seeing here on the left is the mid-infrared image from JWST, and the one you see on the right is the ALMA and submillimeter radio. Now, the ALMA and the mid-infrared image, the features that match each other, that is kind of like what we think of as the Kuiper belt. That's the Kuiper belt analog for Fomalhaut. But what we're seeing for the first time here is the analog for the asteroid belt. So you see another belt inside the outer ring, and then you see the debris disk. This is where this was never seen before. An amazing image. And so now we can really understand, well, why do we want to know something about the debris disk? The debris disk is closer in, and how close you are to the star really changes the chemistry of where you are in the debris disk, which means it changes what kind of planets there are. So we're trying to understand, well, where's the ice line? Where's the soot line? Trying to understand, well, the Earth is carbon poor, so where could have formed? So understanding features like this really give us some insights into the theory of planet formation, to really understand how that happens, and how do planets get built up in these in these debris disk, and as they clear out. Now, as I said, spectra, people gasp at this. So you might say, if I was a young undergrad looking at a spectrum like this, not knowing anything, I would say, that's the noisiest spectrum I've ever seen. There's too many bumps and wiggles. That's noisy. Nope. It is all real. These are all water emissions in the inner disk of a system called PDS-70. And what you see in white is the Webb data, and what you see in blue is the model. All of those features are real features, spectroscopic features from water. And this is not even like, there's just some amazing spectra. We can also study, now water is an important element. It's something that we need. So trying to understand where water is, how does it get into systems? For example, there is water in a main belt comet that was discovered with spectroscopy, yet there was no carbon dioxide. Or was there? Okay, so the question is, I have to look at this plot here. So white is Comet Reed. So that's the JWST data. That is the main belt comet. Whereas comet, the blue one, is the line for a different comet from Deep Impact. And so you can see that there's both a water feature, but Comet Reed, this main belt comet, doesn't have a carbon dioxide feature. So the question is, where's the carbon dioxide? Did it get lost? Was it actually there? Was it vaporizing over time? So there's a lot of questions there, but there's clearly not carbon dioxide in Comet Reed. So that really begs the question, like what's unique about the main belt comet itself? There's also water on Enceladus, here, a moon around Saturn. Let's see, this should be a video. So our team also creates animations about what's happening in these science releases. So there is a giant water plume coming out of Enceladus. So this should play again. And so there is a water torus around Saturn itself. That is a Cassini image, and we knew that there were water vapors, plumes coming out of Enceladus itself. So the question was there anything else that was also coming out of those geysers? And sure enough, there is. This is plume. It's just water too. There's not other elements in there, and so it's feeding this very giant torus that is going around Saturn itself. So this is the blue that you see here. Just play it one more time. And this is the data. This is the Webb data. So water abounds in all these different systems, a very key element for life for us. So the question is there water in other places? So exoplanets, planets around other stars. So I looked it up today. There are 5,573 confirmed planets as of February 5th. Many. I remember when I was working at Regis and I was teaching exoplanets to the students, and I would say, we found 500 exoplanets. And that wasn't too long ago. And then every year, there's 750 exoplanets. And here we are at 5,000. And when the Nancy Grace Roman telescope goes online in a few years, that number will be even larger. And so getting a census of what are the exoplanets, what are their characteristics, we don't know about all of them. That's why we need to study them. Hubble has started to make an understanding of the atmospheres, but Hubble wasn't designed to do that. James Webb is designed to do this. But there's a lot of challenges to understanding habitability around, just habitability. Is this planet habitable? What does that even mean? Well, we know that most planets around red dwarf stars, so let's look at those. But in most cases, the habitable zone is actually really close to the star for these planets around red dwarf stars. Those stars are really active and they have a lot of flares. Okay, so that might mess up the signal. What signal, they're seeing in JWST. The stars are hotter for longer early in their lifetimes. So does that affect the planetary atmospheres? Can these planets even have atmospheres at all? We don't know, and this is why we're trying to study them. We do have some conclusions on some exoplanets, but not for 5,000 of them yet. So we're trying to build up a census of what those atmospheres look like and characterize them. One, if they have them, or if they don't have them, and if they have them, what's in them. So there's all different kinds of planets here forming the formation of all these strange worlds. Hot Jupiters, really big Jupiter-sized planets, but very close to their stars. Sub-Neptunes, a class of planets that's less massive than Neptune, but more massive than the Earth, and then also super-Earths. So what you see on the right here is different. So this is a plot of the planet radius and the temperature of the planet. And what you see in red and orange are the different planets that JWST proposals are going to look at, or accepted proposals are going to look at, and previous data. So we're getting a census of that already. And people wonder, can I take pictures of exoplanets? You can if the planets are big and they're far away from the stars, and we can use a chronograph to block that light. Now this star here, HIP 65426, is 385 light years away. And when it was blocked with a chronograph, an artificial colder on the telescope, you could see the planet itself in different filters with NIRCam and MIRI. So this is one of the first exoplanets to be imaged by JWST. This planet is 3 times further away from the from that star than Neptune is. So these are pretty far away, and usually that's how you can image planets around other stars, is if they're not too close to their star and they're big and they're hot, basically, and they show up in the infrared. But what we actually see more often, it's actually easier to watch planets go in front of a star. So for those of you who might be doing an eclipse event and might say, how does this play out in the rest of the universe? We do this all the time for planet finding. We wait for a star. If it happens to be just lined up in the sense of it goes in front of its star, periodically as it goes around it, we can see a transit, and we can see the light curve, the change in brightness over time, and we could see that eclipse here. And the brightness here can be easily observed. The changes in the brightness can be easily observed as a planet passes in front of the star. So we will put this in the press releases too. Now that light also needs to go through, if you look at this picture, there's a little puffy atmosphere there because the light also has to go through the atmosphere. And depending on what's in that atmosphere, if it has one, because the radiation, the electromagnetic spectrum signature of the star, depending on the wavelengths, the molecules in the atmosphere can absorb some of that out. And we will see the surviving starlight after it passes through the atmosphere. So we can do something called transit spectroscopy get a sense of the light that's left over after the starlight passes through the atmosphere of the star. We can do this with filters, or we can do it with spectroscopy as well. So this just is an example of that. So in some planets, for example, this rocky exoplanet JG486b. So what you see here is a spectrum. The white dots are the data from James Webb, whereas there's two models. One where the star has a star spot and there's a lot of change in the star because of that. There's a lot of change in the spectrum because of the star spots on that host star that the planet goes around. What if there's a water-rich atmosphere? There's a model there. So the question is, which model is really matching the data here? It's too hard to tell. It's possible that maybe it's actually contamination from the star, but it might be water in the star. And this star is actually really close. It's orbiting its red dwarf star in just 1.5 Earth days. It's about 30% bigger than the Earth. So it's too close to the star to be within the habitable zone, but the fact that if there's water there, it's interesting that it can survive that close when the surface temperature is 800 degrees Fahrenheit. So the scientists will be getting more observations to really understand, what is this water vapor that we're seeing? Are we seeing water vapor? If we are, it really gives us an indication of what can survive really close into the host star. Now, you can actually, Webb is so sensitive that if you have a hot planet and it goes behind the star for a secondary eclipse, you can see the very small dip in the light levels due to this secondary eclipse. So this is, which star is this? I can't remember. I'm sorry. I chopped off the frame here. So this is just showing you the star light here is the day side and the star. And then it passes behind the star, and so you get a little dip because you don't get the contribution from the star, the planet anymore, and then it comes out from behind the star and you get it again. So understanding how much light is actually decreased during this time interval. In this case, it's this object here. I think this is TRAPPIST-1b. The decrease in brightness here was watched over 9.7 minutes, and it was just about a small change, 1 part in 3,700. So a very small amount. The data is what you see in blue, but they've been binned so that you can see the change there. This is the first thermal emission that we've seen from TRAPPIST-1b. There's no atmosphere. And so we can measure the temperature based on how the temperature that we see in the in the observations, and really get a sense of that. So it's mostly consistent with it being a bare rock, black body with no atmosphere to circulate the heat at all. So we don't see any signs of absorption of any atmosphere whatsoever for TRAPPIST-1b. This is similar to the results for TRAPPIST-1c as well. So other TRAPPIST planets are currently being observed, and the results from the scientists' analysis have not been released yet. Now, methane is a very important carrier of oxygen because we want to know how planets form, and understanding the carbon and the oxygen in the atmosphere of a planet really gives us clues on how it formed compared to the carbon and oxygen for the host star itself. And so this data here for exoplanet K218b shows us methane without a doubt. You guys can see those bumps and wiggles really, really easily. There's also carbon dioxide here. Now, this is a sub-Neptune. It's about 8.6 times more massive than the Earth, and it's orbiting a cool red dwarf star here. Now, the models that the scientists use to do this retrieval of its atmosphere suggest that this might be a Hycean world where there's a water ocean under a hydrogen-rich atmosphere. But other scientists are using other atmospheric codes too, and they have come up with different conclusions based on their models. So the point here is that doing atmospheric retrievals for exoplanets is really, really challenging. It's really hard, and the signals here sometimes are really easy to tell, and other times they're not straightforward. And sometimes they're only based on one transit when the planet goes in front of or behind the star one time. And so we need to build up more transits to really get a better signal here. Okay, in the interest of time, I'm going to move forward here and talk about more planets here. Ice is on Jupiter's moon, Europa here. So Europa is a moon, and it has one of Jupiter's moons. It has an icy surface, but it definitely has a subsurface liquid salty water ocean, and it's underneath that frozen surface. So the question is, are we seeing anything in that the water underneath the surface here that is changing the surface composition at all? We're interested to understand, what's there? Are there materials necessary for life? We're carbon-based. Is there any carbon here in that ocean, the subsurface ocean? So there's an instrument on the telescopes called an integral field unit, an IFU. Basically, it's a spatially resolved imaging spectrograph. So every pixel in an IFU is a spectrum. And in terms of, for those of you who like to take pictures and figure out what's the field of view of one of these IFUs, it's 3 arc seconds by 3 arc seconds square. So every pixel element on the IFU here on Europa is basically imaging a 200 by 200 square mile piece of the surface. And in this IFU image, you can see a brighter spot. Yes? Yeah, brighter spot there. There's a lot of carbon dioxide there. It's very abundant in this region called Terra Regio. It's a young geological area. It's probably been resurfaced. So what if I look at it in different channels of the IFU? You can see that in near cam image, where there's that bright spot, there's clear signatures of crystalline CO2 at 2.7 microns, 4.27 microns, and more complex CO2 at 4.25 microns. So there is a relationship here between the carbon dioxide ice that's mapped to the bright regions on the surface. Again, there's a clear signature of carbon dioxide, a reservoir for carbon, and it's associated with this young terrain feature, which most likely means that it probably came up from the subsurface ocean. Because this would not be stable on the surface for long periods of time. Now there are plumes coming out of Europa here, and they haven't seen any water plumes or carbon monoxide plumes. Now they're not saying that they found life. It's just a really nice positive indicator that signatures of different compounds and molecules that we think of as being habitable kind of elements that are intriguing to us at trying to learn about the universe are there. My colleague gave a really good analogy. He's like, it's like if you found chocolate chips in the kitchen, you wouldn't automatically say that there are chocolate chip cookies there, but it's promising. And I thought that was really a great way to say, that's fun, right? Like, why are they there? And what could that imply later on? Now, I heard that you are all interested to know what are the science areas that people have been observing with the first year of science operations in cycle 1. So what we see here is, for those of you who are interested, I just put the link here. If you go to Space Telescope, www.stsci.edu/JWST, you'll find this information. So there's all different areas of astrophysics here, from stars to solar systems to star formation to early galaxies. And you can see that for the approved programs in red, exoplanets and galaxies were the largest percentage of all the observations. And the same is true for cycle 2, which is the current cycle that we're in. About 75% of the observations that JWST has taken is mostly spectroscopy, because that is where we learn the most about what's happening in the universe. The images are great, and there's definitely things that we need to study using the images, but if we want to get into the details, the stories and those details in the spectroscopy. So I think I will stop with this slide, which is, there are so many, this wasn't an outreach talk in the sense of there's lots of resources for you all to talk about JWST when you're out standing at your telescope or giving a talk before your telescope activities. So this QR code takes you to webbtelescope.org/resource gallery. And I'm so proud of these assets, these outreach resources. I worked on many of those that you can use to share. And for those of you who have web virtual, if you have a VR headset, we have web virtual reality for you as well. A very fun outreach event for kids. I'm actually, I think, when am I using it? I'm using it soon. I'm using it in a couple of weeks myself. And you will have a line of kids waiting for web VR. So thank you very much for your time. And I'm going to open it up for questions. Thank you.
Well, thank you. Thank you, Dr. Hart. We really appreciate that. Can you stop sharing your screen first so I can see hands online? First of all, I want to say a couple of things. Do we all remember if we watched Star Trek and we saw them going to all these places, all these systems that had all these planets, and we thought, oh yeah, right. Because we didn't think they existed back then. And now we know they did. That's pretty exciting. And another thing you made me think of is I was listening to Astronomy Cast a month or two ago, and they were talking about how scientists were trying to wrap their heads around how they were going to classify these planets, because they were like, well, are we going to call them sub-Jupiter or super Earth, or, you know, and I think they finally have found a way to kind of try to classify them all, right?
I will admit, in the beginning, exoplanets wasn't in my area of research. Yes, classifying, I personally classify it as, I do the most simple. Are they more like Jupiter? Or are they more like the Earth? And there's
okay.
so I'm interested to know, with gas giants, there's an atmosphere. The rocky ones, we really want to know, do they have atmospheres? Don't they have atmospheres? But for the gas giants, we were also curious, what's in their atmospheres? How are they different? Because the chemistry of their atmospheres does give us indication of their formation history, and we want to know how planets do form. And these are already formed planets. So taking studies of the fully formed planets and trying to understand the protoplanetary disk situation as well, like in the Fomalhaut, like how do we get from protoplanetary disk like the L1527, where it's really young, and there's so much material there, to something being cleared out a little bit like with Fomalhaut, and then getting to these fully formed systems. That whole story of planet formation, there are so many gaps in there that each piece allows us to get a better understanding of that. And we do not have a complete census of we don't have a complete census of all the galaxies, all the planets out there and their atmospheres. So being able to do it for the first time really well with JWST, people are this is what they're excited about in exoplanet science, is really understanding those atmospheres. In whatever they say.
Yeah, I'm sure that's going to be the case for a long time to come. So the first question I saw come in the chat was a little bit ago from Mehmet Unsoy. He says, how is the observing time managed for Webb, for JWST?
Yeah, great question. I don't have the numbers off the top of my head, but I can tell you how it works. So there is a certain amount of time that's allocated for the competitive process of putting in proposals. That number I don't have off the top of my head, but there is a set allocated amount of time. And if you go to stsci.edu, and while we're talking, I'll drop it, /JWST, some of that information that I was sharing, like key points from the JWST meeting, all those slides are available. One of those slides has the amount of hours in it that you can get. In terms of, so that's how, so first it's, there's a set amount of time, and there's only a set amount of time, yet we have lots of proposals that came in. So the whole vetting of what gets selected is done by the Telescope Allocation Committee, where community members review the proposals and they rank them, and they identify what rises to the level of using this telescope. And so the oversubscription rate, I think, is probably 1 to 10 in this cycle, I believe. So all the proposals are amazing, but they have to float up to that 10%. And so that process is done by the astronomical community, and then they're approved by the director's office at Space Telescope Science Institute. There's also time that's been set aside for programs, scientists, and they're guaranteed observing times, GTO programs, or early release science observations that happened in the first year of science. Those were all time that was given to certain science teams because they helped with the development of the observatory, and so they were given that time. So a lot of the solar system time was part of Heidi Hamel's program, and then she gave that time to different science people in the science community to do that work, but it was guaranteed for her program, so it didn't have to go through that competitive process. But those teams also did a lot of work before Webb was launched and commissioned.
Okay, thank you. I did put that link in already, but I would like to get your permission to put in that QR code and maybe some of the other links that were at the end of your
You know what? I'll drop it
presentation.
in. I'm a good multitasker, so I will drop it
Okay,
in
good.
as I answer questions, and then you'll have it in the chat. Does that work?
Okay, very good. Yes, I see that Mike or Jinky Gardner have their hand up. I'm not sure which one of you. Go ahead.
Mike. It's me. Very outstanding talk, and thank you very much. A couple of quickish questions. You talked about you talked about the density in the pillars, for instance, or the pillars that we couldn't see through even with the Webb. How dense is the material there?
I do not have the column density at the tip of my tongue.
Okay.
But it is cold enough that is not emitting in the mid-infrared. So it might be emitting in the far infrared. I don't think it is. And yes, I don't think I have an answer for far infrared or radio, but definitely in the mid-infrared, like the coldest should even emit a little bit of mid-infrared, but it's not. It's just too dense.
How do you define dust? You were talking about dust in the supernovas where they destroy.
Yeah. So dust is usually, so astronomers talk a lot about these complex polyaromatic hydrocarbons, which are very complex chains of carbon-based molecules with other elements attached to it. In some cases, these PAHs don't even have a structure really known for it, but they know that they have signatures that are all in the sensitivity of JWST. So if you're interested in understanding star formation, which requires a reservoir of dust and gas, you can use JWST to observe star formation not only in the nearby galaxies, but redshift it out into, if it's in the near infrared, if you're looking, I'm sorry, you can see it in even more distant galaxies, 1 billion light years away, a few billion light years away, because that dust is, it's more complex than carbon dioxide or ethanol or methanol. In some cases, actually, and this dust is also solid too. So there's solid forms of dust. There's gaseous form as well. but they're complex molecules. Good question, thank you.
Do we have any questions in the room here? Okay, Ernie, why don't you come up here so she can hear your voice? Just tell me. Okay, Ernest Sinelli wants to know if JWST has looked at Betelgeuse yet.
My guess is no, because it's probably too bright and would saturate.
Oh, okay.
That's my educated guess, but I don't know for certain. So I'm going to do my multitasking while you guys are talking because I can look. So one of the things, so if you get, I'm going to actually just share. I'm going to share my screen, so I'm going to show you how I can tell really quickly
Okay.
whether
Very good.
it has or has not. So let me share my screen.
She
Share.
has super access.
Yeah, well, it's not super, it's actually for everybody. So, oh, sorry, let's see here. I don't know what's showing. Okay, there you go. Okay, so I know why I'm gonna go here. Okay. So one of the things at the Space Telescope Science Institute is that we are also the archive of space telescope data. Hubble Space Telescope, James Webb, Spitzer's in there, TESS is in there. So if you type in MAST, but oh, it's actually the first one. Okay, MAST. It's the Barbara Mikulski Archive for Space Telescopes. So if you ever want to download the actual data from the observatory that's gone through the calibration pipeline that's developed at Space Telescope, this is where you can download it. So I think from here, I might go to search tools. So we can go to, they've just released a new one too. I'm going to use the old one, the MAST portal. And I will type in Betelgeuse. I could spell it right.
USE.
Yeah, thank you. All right, I hit enter. Oh, I spelled it wrong. Did I spell it
It's
wrong?
GEUSE.
Thank you. EU. And that's what I thought. That's what you said, but I didn't type it. So. All right, so you type it in, it should resolve the coordinates. And what you see is a sky map here. There's lots of things going on there. What I do is in here, I look at the mission, I open it up. Do I see JWST here? No, it has not been observed by JWST, but it has been observed by HST, IUE. For those of you who know IUE, that was like the very first telescope that I took data from as an undergrad. Galax is a UV telescope. There's TESS and Fuse as well. And then OPO, this is an old thing. OPO is the Office of Public Outreach. In the past, they used to catalog things as outreach. So no, I've answered in real time that it has not observed Betelgeuse.
Thank you.
Yeah.
Yes, Chris, go ahead. He's coming up to
Sure.
ask himself.
So you're so when you're observing a planet transiting in front of a star,
Yeah.
and I look at the atmosphere of it.
Yeah.
You're talking about the light that's going through the atmosphere.
Yeah.
But we know that here on Earth, the atmosphere is bending the light a lot. So like the sun sets apparently much later than it actually would if we had no atmosphere, because the atmosphere is bending it in so much.
Mm-hmm.
So how hard is it to take account of that? And like, seems like the light, when the planet's right in front of the star, most of the atmospheric light would be bent out away from us. We wouldn't see it. We might see more of a signal over when the planet's near the edge of the star or off the star a little bit, where we're seeing more light coming through the atmosphere being bent towards us
Like
by the edge.
So as I understand the observations, they're timed pretty well to know when the planet will go in front of the star. They don't turn on the observations like just on time. They have to make sure they catch the transit. They don't want to miss it. So thinking about, I do have a ball in front of me here. So if you think about, Fred, I feel like I'm in class. So as the planet marches in front of the star, when it's there's going to be a part where the atmosphere, the thickness of the atmosphere, like if it's a rocky planet, you're just going to get the light through the atmosphere before what you're talking about here. And that's not fast. These transits take several hours. And so what I think they do is that they're able to get the data when the light is mostly going through the atmosphere. And they can do this observation in many different filters as well. They also can do spectroscopy here. So they are a lot smarter than me. And they can do a lot of, I've seen the traces of some of these exoplanet spectra on the CCD chips. I'm like, how do you extract it out of there? So there's a lot of tools that the astronomy community needs to do that's very specific for JWST. But the challenge here is that you have to look at the signal before the atmosphere is in front and the signal after it's just the starlight to figure out where the decrease is as a function of wavelength. And then you have to figure out, well, is this a real feature according to a model that they're using to fit to the spectrum that they're measuring? And it's not just one model that the whole exoplanet community uses. There's many different kinds of models for gas planets, for rocky, atmospheres around rocky planets, what's going on in the surface. And so this is that challenge of trying to understand these exoplanets, knowing that there's information they do know before they're trying to look at the atmospheres, but also the data. So the JWST data, in some cases, they get it like right away. And that's what we had to do for Webb's first images. They picked a target where they knew they could get it right away and not have any issue with just one transit. That is more challenging for some of these targets like TRAPPIST-1.
Wonderful, thank you. Jack, I see your comment. Superb presentation, many thank yous.
Oh, thank you so much. Thank you for the kind words.
Yes, Mehmet, go ahead with your question.
Thank you. This is a great presentation. Thank you very much.
Oh, you're welcome.
I have two questions. One related to the previous question, this transient spectroscopy of the exoplanets.
Yes.
As the atmosphere of the exoplanet is observed, do you know whether any of the exoplanets exhibited similar atmosphere, like nitrogen and so forth, like Earth? Do you know any of those planets?
Of the ones that I'm aware of. So that is the what is it? They call it the $5 million question. What rocky planets have atmospheres? So with TRAPPIST-1, the two planets closest in the TRAPPIST system, those are rocky planets, and there's no evidence of any atmosphere. So going back to the question, how do I know there's an atmosphere? Astronomers talk about like it's a flat, like the transmission spectrum is flat. There's no absorption of anything. There's nothing there, like there's nothing there to absorb. So there's no features in the atmosphere that come out of transit spectroscopy. And they say that the spectrum is flat, meaning there's no signature. And so so far, there's no atmosphere around those rocky planets. The GJ one that I showed earlier, there's possibly water vapor there, but they don't know if it's from the star or it's from the planet. So they need more observation. So that is a tantalizing conclusion. If any astronomer who's studying rocky exoplanets says they find something that's like the Earth, it's really hard to do, to find an Earth-like atmosphere around a rocky planet. I recall for one of the outreach projects I had to work on a couple of years ago, I remember reading in the papers that the simulations of trying to get a concrete detection around an Earth-like, an atmosphere like the Earth would require definitely more than one transit. I want to say it's in the 10s to 50s. It's only the second year of science operation. So there's not that many transits like that.
I understand. Yeah. The second question, Doctor, is out of that 700 papers that you mentioned,
Mhm.
what is the majority on? Do you know?
Oh gosh. There are lots of early galaxy papers.
So that's what I thought.
There's
Early
lots.
galaxy is the initial focus then.
It is. People are really, really interested to know. It once the data from JWST became public from the first images, there was the very first image was unveiled by President Joe Biden, and is the deep fields, Webb's first deep field. People were trying to do science on the pictures, and as soon as the data came out, people were flurry trying to figure out, what am I seeing? What am I seeing? It's very cool things in there. And so that excitement, that looking into the details of those galaxies. Where are they in the universe? How far away are they? What's their luminosity? What's their shape? What's their size? There's a lot of information in there that can't be done by hand. And people are finding this data now, like I'm trying to understand, like there's just a recent news release about the shapes of all these galaxies. They're not like beautiful elliptical galaxies, right? But we don't expect that in the early universe. So what is this telling us about that formation history at that time? We are getting the first glimpses. And so a lot of the papers really reflect a lot of this early time, because we haven't looked at it. We've never seen it before. We are really...
As opposed to within the solar system observations, like water on some of the moons.
Oh yeah, there's lots of interesting things on the solar system as well. But those, I'm biased. I love galaxies far away. There are way more galaxies than there are planets. That's just my opinion.
Okay, thank you very much.
Yes, you're welcome.
Thank you. We do have another question here in the room. Do you want to come up?
Sure.
Just a moment while he comes to the,
Mhm.
we had a Navy incident here, so we don't have a hand mic here.
No worries.
Hi, my name is Daryl. Thanks for that presentation.
Daryl.
It was amazing. I'm just wondering if you could say a few words about how the day-to-day mission planning of the satellite goes and how complicated that is, and you know what the ups and downs are, how things are played off. For example,
Go ahead. What was that?
is it just a simple factor of the subdividing the time, or are there various resource
Oh.
issues and so on?
So we have there's the Mission Operations Center, so the health of the observatory, command and controlling, making sure that's all working as expected. So that we have flight engineers who do that. Then we also have the people who are tasked with making the schedules. They run a really tight ship. So we have to include not only the actual observations, but the overhead that's associated to slewing the telescope, taking calibrations and things like that. So at the same, I'm gonna put into the chat, you can actually see the observing program for the next 2 weeks. That's posted, that's a publicly posted piece of information. And you can see what's being, let's see, where is it? Program information. I'll drop it in before you guys close the chat out here. But that observing schedule is there. So they do plan as best they can to use every piece of time to schedule the observations. One piece that did change after the start of science operations was there was one large micrometeorite hit that was above the expectation. And so they've been monitoring that pretty religiously, because they want to make sure it doesn't change the sensitivity of the telescope. Because of that, so these are, there was modeling for these micrometeorites. And so there is something called the micrometeorite avoidance zone now, called the MAZ. And so when observers make observations, they have to make sure that their observations are not in the MAZ, or the schedules will make sure that it's not in the MAZ, to really reduce any micrometeorite hits. And it's like we're just not going to drive the telescope into the rain. We're going to go in the other direction to avoid any extra, potentially extra hits. And so the schedulers also make sure that that happens as well. I do not know all the details on the back end, but they have lots of planning software to make sure, hey, they know what the slate of observations are for cycle 2 that just began in January, February. So it began in July. So we're into cycle 2. We know what the slate of observations and targets are, and they fit them in the best way they can. Stuff moves around. Scientists can also submit proposals for director discretionary time if they have like, hey, there's something just happened and we have to observe it with JWST now. Like they're like, people submit those kinds of proposals. And so if something like that happens, then they might reschedule some other observations to make that fit in. In terms of the day-to-day, there's a data downlink from the telescope to the DSN at least once a day. The timing of it changes depending on what antennas are available in the Deep Space Network. There's 3 main telescopes, and I can't remember, in Madrid, Australia, and in the US. So there's always, an antenna at one of those stations for when we're ready to download data. But Webb is not the only thing out in space, so there's time that needs to be figured out with antenna usage to get that. And that's the other things with scheduling. Yeah, I think that's it. That's what I can share now.
Okay, thank you very much.
Mhm.
There was something else that crossed my mind and I think it went in and out.
That's okay.
At
Well,
any rate, one more
I'm happy to
question.
take more questions. Oh, here's the observing schedule.
I think I can have one more. Go ahead, Chris. Come on back up.
Hopefully this is quick.
Yeah.
How far away from the sun to Webb axis can the Webb observe? So there's going to be some hole above the ecliptic and below the ecliptic where it can never observe.
Glad
Right,
you asked
so-
that question. So it's called the field of regard, what JWST can see at any one time. So it always is pointed away from the sun because the sun is a giant infrared source and we will fry out in instrumentation. So that's why JWST has the 5 layers of sun shields to keep it cool on its side, and it can stay hot on the other side. So I remember this number before. I won't pull it out at the tip of my. The side that faces the sun is as warm as what you would want to warm croissants in your oven, which I warm mine at 210 degrees Fahrenheit. So that's how hot it is on the sun side. On the other side, it's much colder, and I can't remember the number off the top of my head. So in terms of so if this palm of my hand here, I'm going to use my aids here. If this is the sun, and actually, oh, it doesn't matter. This is the sun. This is the sun shield. So the telescope's on this side here. So the observatory here can spin in all different directions, but only face the other way. It can tilt this way a little bit as well. And so it actually can see this part of the sky the whole time. And then as it goes around here, so it can actually see above what you were talking about. Like it sees a part of the sky up there and down there because it can do this this tilt. And we have an outreach product that goes through the field of regard to answer exactly that question that you asked.
I did think of my question, and
Yes.
that is, have they recalculated based on the amount of fuel on board the life expectancy of the mission?
Great question. Yes. And let's see. So the mission was designed to have I think it was slated for a 10-year life expectancy. The launch on Christmas Day 2021 was so perfect. And the orbital insertion at L2, all the different burns it needed to do to get into the L2 were perfect. That it actually extended the lifetime by almost 2. And I believe that the NASA line is that there's more than 25 years.
Wow.
Yeah.
What a gift.
And I can't remember,
After
I
all
can't
that
remember the exact number,
waiting.
so I'm using more than to be safe. Yeah.
After all that waiting, it'll be worth it.
Oh my gosh, it's a lot of people. I was, one of the stories this was when there was a surge of COVID. And as I mentioned, 30 minutes after launch, all the controls were going back down to Space Telescope. So there was going to be a huge media presence there. And I was supposed to be there helping people move around, being in the building. And I was very sad that I wasn't able to do that. But it was needed because it was, it was a very trying time. And so I watched it at home, as if you guys watched it at home, I did the same thing. Yeah.
Wonderful.
And I
Well,
will
thank you. Thank you so much for being
you're
with us
welcome.
this evening. We really appreciate it. It was a wonderful presentation.
Oh, thank you so much. Yeah.
All right.
If I'm ever in Colorado and can give, I know where you guys are. So
That's right. You do.
I hope to be able to make a in-person meeting in the future.
We would love
Thank
to
you
have you.
again for all your questions and the invitation.
Thank you so much. It's been a real pleasure. All right. Now we are going to proceed to the results of the election. Greg Fogarty, you are up.
Thank you, Dina. So the results of the elections are in. So I'll pass on my congratulations to all the winners. And I shall quickly read out the results. And I'll start with the E-Board. So the E-Board members who are elected are Bill Cast, Ron Aranak, Joe Gafford, Jack Eastman, Joe Goodwin-Austin, Steve Barr, John Bickle, and Mark Chrisman. And they're not in any particular order. The secretary goes to Toby Sheets, and not with any surprise, the new president will be Doug Triggs. So congratulations to all the winning candidates.
Greg, I want to thank you for stepping in to be our election coordinator this year. Very good job, and very grateful for doing this. I know we only had one little bit of a race there, but it's still quite a job, and I appreciate all the work that you put into it.